All right, so let us have a look at a little bit of revision of what we have been doing. So I'm going to share the other screen. All right, so remember with matrices, there's a whole array of numbers, and you had a specific amount of rows, specific amounts of columns, and I said to you that one of the uses, or one of the many uses, but quite a primary use, was to solve systems of equations. So I gave you equations that were simultaneous equations, and we set them up, and I said, you can solve this normally, that's very nice. However, what happens when you have something slightly more complicated? Well, that's when matrices really come into effect. And we found that if I want to refer to just one bit of the matrix, that is known as an element. And then we had a look at our four operations, our addition, subtraction, multiplication, and division. So with normal numbers, it can work perfectly fine. With addition of matrices, you add each element by element. If you have subtraction, you subtract each element by element. When you come to multiplication, boom, everything exploded. And then we found that it all depended on the dimensions of the matrix as to if you could even multiply. Remember that we had to make sure that these two inner dimensions were equal. Remember, dimensions were rows by columns. So here, this matrix has 2 rows and it has 3 columns. All right. Okay. So then, we had a look at this and we saw those weren't equal, but if we swap them around, we could therefore multiply because this became a 3 by 3 on the middle, and then my resulting matrix is the 2 outside dimensions. So because this is a 2 by 3 and a 3 by 2, the 3's are equal in the middle, and the result is a 2 by 2. So then we came to finally saying, well, how can we use this knowledge to solve a system of equations? And what you do is you need to take the matrix you need to know the matrix of coefficients. So you take the coefficients of all of these, so 1, 1, 1, minus 1, and that becomes a 2 by 2 matrix. And over here, you can put your variable matrix or vector, shall we say, because it's a single row, a single column. Here it's a single column. And if you multiply these two things, it actually gives you x plus y, x minus y, which is my system of equations on the left, which means that I'm totally in my right and it is totally valid to be able to split it like this. And the reason I'm doing this is because we need to try and get rid of this to just leave x, y on the one side. But how do we do this? Well, we need to know a little bit extra to say, well, here we have a 0 matrix as well, which is just a whole bunch of zeros together. And anything times by 0 gives 0. But it doesn't just give a 0, it gives another 0 matrix. And then we have the 1 in matrix algebra, which is your identity matrix, symbolized by an I, which is all zeros, except it has 1s down the diagonal. And if you multiply anything by 1, you land up with itself. As you can see here, this times by the identity matrix gives itself. So now we needed to try and work out how do we do division of a matrix, and we found out that we couldn't. Division with matrices is not defined and it is not possible, which is very sad. However, if you multiply by the inverse, that is defined because multiplication is defined. So we then had to work out the inverse of a matrix. And to calculate the inverse, we had to take 1 over the determinant of this matrix, and the determinant we calculated as the product of the diagonal minus the product of the off diagonal. And then you swapped the main diagonal values and just made the off diagonal values negative. And there is a reason why you do all of this, and it is far more complex maths that I'm not going to give you guys yet because you really don't need to know about it. All right. So what we did was we actually solved this. So we found our inverse, we found our determinant was -2, we swapped our diagonal, we made the off diagonal negative, we multiplied this value in the front in, which means we multiply it to each element. And we saw that if you take this inverse, which is this, multiplied by my original, I get to my identity matrix, which is the whole point of it. Because remember, the identity is 1, and 1 times anything gives itself, which leaves us just with our xy, which is what we wanted at the beginning. And then, because we multiplied this at the beginning, which is known as pre-multiplying, we need to put it at the beginning on this side. If you put it at the end, the dimensions wouldn't work, and therefore you wouldn't be able to multiply. So we multiply this, we got a 2 by 1, and we came out with an answer of x equals 2 and y equals 1, which is exactly the same answer that we got at the very beginning, showing you that all of this long method actually works, which is quite amazing. But you know, it's even more amazing. Matrices don't stop there. You say, what? You can do something more with matrices, but matrices are so cool already. If only I'd known about this before. Ha 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 ha. I know. So what we can actually do with matrices is also transformation geometry. So we remember transformation geometry as reflections. We remember it as translations. We remember it as rotations. And we remember it as enlargements or reductions. All of these fun things you can do with matrices as well. So, the big thing with this is we need to remember on a Cartesian plane. Let me just get that line a little bit better. That's a little bit better. Y, x. Any point on your Cartesian plane can be specified by an x and a y coordinate. But when dealing with matrices, matrices are essentially made up of a string of vectors. So just as you have multiple elements, if you just look at one of them, that becomes a vector. Now, how could we have a look at this as a vector? Well, you just draw a vector. That's nice, that's not complicated. What am I making a big deal about? Well, this is actually the resultant of two vectors. So it is a horizontal vector and a vertical vector. So some of you that aren't doing science, you may be a little wavy on this sort of stuff. You don't need to worry too hard about it. But the most important part of this is that essentially every vector that you write or that you draw can be broken down into a multiple of unit vectors horizontally and unit vectors vertically. So that's 1 and that's 1. So this vector over here is a 1, 0 vector because just like we put x and then y in coordinates, we put x and then y as vectors. This vector over here would be a 0, 1 vector because my x value is 0 here and my y value is 1 here. My x value is 1 here and my y value is 0 here. So we need to do any transformations, work on these base vectors, and then we can actually work out what the change is going to be. So you might still be thinking, what is he talking about? So if I want to, let's do something very simple. What about if we reflect about the y-axis? What's going to happen? Well, what's going to happen is absolutely nothing to my vertical axis. my vertical vector. But this vector is going to change. So I'm still going to have my vertical one over there, but this one is now going to be reflected about the y-axis. So this is now going to go over there. And what is this vector, therefore, going to be? So this vector, remember x and then y, my x value here is -1, so it's -1. My y value is 0. So when I initially had my two coordinates, which were the horizontal one first, so it's 1, 0, and 0, 1, you're like, that looks familiar. Maybe this kind of looks like your identity matrix. To reflect it about the y-axis, it needs to become -1, 0, and then this one, which is still 0, 1. You'll be like, all right, I kind of get what you're doing, but like, how am I going to use this? What is it? Well, let's actually put some coordinates and see how we can actually do this. So imagine that we had a triangle, all right? So my triangle here, this has coordinates of 2, 1. This has coordinates of 5, 1. And this has coordinates of, let's go nice middle, 3, 3. All right. Here are my coordinates. And I want to reflect these coordinates using a matrix to the other side of my y-axis. How am I going to do this? So, first thing we got to do is we got to make space. Actually, you know, it would be quicker just to get rid of everything. All right. So let's quickly redraw. 1, 2, 3, 3, 3, 2, 1, 5, 1. Great. Now, when I write these coordinates as a matrix, I still need to write them as a vector downwards. So I'm going to call it A, B, and C. It doesn't matter what order you name them in, A, B, C, or what order you put them in the matrix. It doesn't matter as long as they are vertical. All right, so I'm going to put them as A, then B, then C. So A is 2, 1, because remember, you always put your X here and your Y here. Then B is going to be 5, 1, and my C is going to be 3, 3. So this is my matrix of coordinates. This matrix I need to multiply by my transformation matrix. Remember, my transformation matrix was -1, 0, 0, 1. Now the question is, do I multiply this by that or that by this? Hopefully you're not saying, it doesn't matter, it's matrices, it's fine. It's not fine. Remember, this as dimensions, and it's so important I'm changing colors, this as dimensions is a 2 rows by 3 columns, and this is a 2 by 2, not equal, can't multiply in that order. So we have to swap them around. And therefore, we need to make sure always, irrespective of how many coordinates you have, you always put the transformation matrix first, because that way you will always have the right dimensions. All right. So you put transformation matrix first. So -1, 0, 1, 0, 1. My matrix of coordinates 2, 1, 5, 1, 3, 3. And once again, just to be sure, I'm going to check dimensions. Okay, great. 2 by 2, they are equal. Therefore, the resulting matrix is going to be a 2 by 3, which we would expect because we are looking to get new coordinates. So it has to be the same size as the coordinate matrix. Now remember how we multiply. We multiply across the left, down the right. So I'm going to multiply it -1 times 2 plus 0 times 1. Then going down, it's 0 times 2 plus 1 times 1. So 0 times 2 and 1 times 1. So we're going across there on the left and down there on the right matrix. So then we move across a column. We go -1 times 5 plus 0 times 1 and 0 times 5 and 1 times 1. And then we move across a column again. 0, no, I'm looking at the wrong row. -1, 1 times 3. So -1 times 3 and 0 times 3. And then we have 0 times 3 and 1 times 3. Hopefully no one is struggling with that matrix multiplication because we've done that a couple times now. And then we can simplify this. So that's 0, that becomes -2. That is 0, that becomes 1. Over here we have -5. Over here we have 1. Over here we have -3. And over here we have 3. So let us compare these coordinates. Because remember, the columns are the coordinates. -2, 1. Well, that's over there at -2 and 1. This one is -5 and 1. Over there, -5 and 1. And then this one is -3 and 3. -3, 3. Over there. And just as you're expecting, it is a perfect reflection about the y-axis. All right. So this transformation matrix is crucial. And it all depends on what you want to do as to what this matrix is going to be doing. All right. So let's have a look at a couple of our options that we have. So we've done our reflection about the y-axis. That was -1, 0, 0, 1. Remember, there's my one vector, there's my other vector. If I reflect about the x-axis, which is this way, this vector is not going to change. So that one is going to stay the same. I need a new color. So that's still going to go to 1. But this one is going to change now down to -1. So remember, I always list my x first. So that is still a 1 and a 0. But now my y is different. This has now got an x coordinate of 0 and a y coordinate of -1. Because it's a lot of matrices to try and learn with all the reflections, all the rotations. A lot of them are very similar. But if you can actually understand how to work them out, you could very quickly work this out and then get it. If you're reflecting about the line y equals x, there's my two starts. There's my y equals x. And then what's going to happen? Essentially, they're going to swap positions. So this one, or we start with this one. This one, instead of being a 1, 0 vector, over there is going to become a 0, 1 vector. And this one is currently a 0, 1 vector, but when it goes down there, it becomes a 1, 0 vector. So you can literally see they've literally swapped. If you're reflecting y equals minus x, you're going to put negatives. What about if we do a rotation? Let's do a rotation before we have to stop. Let's do a rotation 90 degrees that way, clockwise. Yo, that took me far longer than it should have. All right, 90 degrees clockwise. There's my one. There's my other one. Now I'm rotating 90 degrees clockwise. All right. So that means that this vector is going around and is going to go to there. And this vector is going around and is going to go to there. So how are we going to write this? Well, this vector is the one we mentioned first. And this one is therefore going to become a 0, minus 1. And this one, we're going to go down to there, and that becomes a 1, 0. And the amazing part is you can actually try this with any coordinates you make up, as I just did. And it will always work. And it doesn't matter how many coordinates you list. And that's one of the nice things is you previously would have had to have done it bit by bit by bit. Taking this coordinate, reflect. This coordinate, reflect. Draw them out, see what they are, flip it over, have a rule, etc. Like this, if you have 20 coordinates, you can plug it into a computer. The computer multiplies the matrices. Boom, there's your new ones. And you go plot, 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 plot. Thank you very much. Which is quite amazing, actually. So the uses of matrices are stupendous. And I'm literally just scratching the surface of the uses here. So once you get into university, you start dealing with a whole bunch more and a whole bunch more intense stuff with matrices. And it really gets really, really cool.